The third problem I want to take up here is we have a string mu connected to another string mu1 and then back to mu again. So this is at x equals 0, this is at x equals L. Again, the question is to find the reflection coefficient, namely the percentage of energy that is reflected back and percentage of energy that moves out. And this is interesting. Before we discussed two semi-infinite strings. Now there's a finite length. So there are two discontinuities. And there are three regions. 1, 2, 3. And at each region, wave equation is solved. Invariance in this problem, omega and tension. So we write each y as some psi of x times e to the minus I omega t, and each psi satisfies plus k square psi equals 0 in its domain. So the solutions, psi 1, the first one is I have an incoming wave e to the I kx plus reflected wave back r e to the minus I kx. The second one, so this is for x in this region. Psi 2 is again, must solve it here with k1. So I will write it as a cosine k1x plus b sine k1x. This is 0 x alpha. And the third one, psi 3, is t e to the I kx. There are four unknowns, r, a, b, and t. And if we ask the question how much of it is reflected, how much of it is transmitted, we are really looking for these. And so we need four equations. We have them. At x equals 0, the displacements must be the same. And the space derivatives must be the same. That gives two equations. And here, displacements must be the same, space derivatives must be the same. So let's write the equation corresponding to these boundaries. Psi 1, 0 is equal to psi 2, 0. That is 1 plus r. If I put 0, sign is gone, I have a. The second one, psi 1 prime 0 is equal to psi 2 prime 0. This gives me ik 1 minus r. Now take the x derivative and put x equals 0. This gives sine. Sine x is 0. At x equals 0. This gives me cosine. So that's equal to k1 times b. So we have two equations. At x equals L, psi 2L is equal to psi 3L. This gives me a cosine k1L plus b sine k1L. That's equal to t e to the I kL. And the derivative psi 2 prime L is equal to sine 3 prime L. This gives me now minus K1A sine K1L plus K1B cosine K1L. That's equal to IK. I'm taking the derivative of this at x equals F, e to the IK F. So 4 equations and 4 unknowns, and we are really interested in finding R and T. So first, there's a T here, T e to the IK. So we can replace this one with that. This just gives me an equation with A and B. But A and B are given in terms of R, so I can solve for R. It is simple in principle, but we need to do some algebra. So let's begin. I am starting here. Minus K1A sine K1L plus K1B cosine K1L is equal to IK. Instead of T e to the IKL, I am putting this entire thing. IK A cosine K1L plus B sine K1L. Let us collect A is on the left, B is on the right. Minus K1A sine K1L minus let me just take into minus A parenthesis minus A K1 sine K1L. This becomes now plus IK cosine K1L. That's equal to B IK sine K1L minus K1 cosine K1L. Now, I will replace A and B by those values. Let me erase these. We don't need them anymore. We don't need the figure even. We can draw it later if you wish. Minus, instead of A, we write 1 plus R. 1 plus R. K1 sine K1L plus I K cosine K1L. That's equal to B, and B is IK over K1, 1 minus R times this part, IK sine K1L minus K1 cosine K1L. So let us collect R times a coefficient equals to something, and then we just divide, we get the R. But let me multiply this thing by K1. So this is K1 square, IK K1. Okay. Now, R parenthesis. This is minus K1 square sine K1L minus ik k1 cosine k1 L. This gives me minus k square multiplied by minus r is plus, taken to the other side is minus. So it is minus k square sine k1 L. And this minus minus plus, taken to the other side is minus I k k1 cosine k1 L. This thing will be equal to the constant terms. First is minus k square sine k1 L minus k square sine k1 L minus ik k1 cosine k1 L this was minus, it goes to the right, becomes plus, plus ik k1 cosine k1 L only one term is left, this one, 1 minus plus k1 square plus k1 square sine k1 L. So this knocks it off. Every term has a minus sign here, so there's an overall minus. So we change the sign. So R is finally k square minus k1 square sine k1 L divided by k square plus k1 square sine k1 L plus 2i k1 cosine k1 L. Notice that again, if k is equal to k1, namely mu, mu1, mu, if they are all the same, then k is equal to k1 and this drops. Let us take a shortcut. Let us find the reflection coefficient and from then the transmission coefficient. I am erasing everything here. Assuming this is correct, I'm erasing everything. So, I incident average is 1, that's then 1/2 omega tension times k, and I average, time averaged energy current reflected is R square 1/2 omega tension times the same k again. So if we divide the reflection coefficient is just R absolute square. So let's take the square of it. K square minus K1 square K1L divided by K1 square plus K square plus K1 square sine square K1L plus 4K square K1 square cosine square K1L. It's since everyone has a sine square here, let's write it in terms of sine 1 minus sine square k1l. So it is minus 4. This is plus, so it makes a k square minus k1 square square. So r is k square minus k1 square sine square k1l divided by 4 k square k1 square plus this is 2 k1 square 2 k square k1 square. This is minus 4 k square k1 square. So it is k square minus k1 square square sine square k1l. All right, so this is it. Reflection coefficient is this. When k equals k1, r is 0. Now, I will claim if this is the reflection coefficient, then transmission coefficient, is 1 minus r, and 1 minus r is easy because this term is just that term. So this gives me 4 k square k1 square over this whole thing, 4 k square k1 square plus k square minus k1 square square sine square k1l. Or I can divide this by the numerator, 1 over 1 plus k square minus k1 square over 2k k1 everybody square times sine square k1l. We are finished. That's the t. Of course, we did it in a quick fashion, namely we did not compute t, we did not compute namely the transmission amplitude, we did not compute this thing, namely we did not obtain transmission from here, we simply looked at it that way. We did a shortcut. I am erasing this part. Let us now discuss this transmission coefficient. Let me write it again. I will focus on t now. T equals 1 over, I am writing this again, 1 plus k square minus k1 square over 2k k1 square sine square k1l. It doesn't look a very, I will erase everybody now. Let us consider when t is 1. T is 1, t equals 1 when, well, if k is equal to k1. But that's the trivial thing. That's there is no this intermediary mu1, mu. That's the trivial solution. So it's a good thing that our mathematics gives us that result. But beyond that, however, it is 0, t is equal to 1 and the reflection coefficient is 0, transmission coefficient is 1. When k1l is k1l, sine k1l is equal to 0. That means k1l is equal to some n pi. N equals 1, 2, etc. That means 2 pi over lambda 1, L is equal to n pi. then n lambda 1 over 2 is equal to L. That means, again, this is our mu1, 0 to L. So when we have, for example, this is L, the length of this thing, when there is an integer number of, this is L, integer number of half wavelengths of the wave on this bit of string is there, then sine KL is 0, then transmission is 1. Let's write this equation in another form. So integer number of half wavelengths of the wavelength here, if that fits in, then we have a so-called transmission resonance. Let's have a, one should really do it on the on something like MATLAB or something. But let's write K1 is equal to X times K. So T is equal to 1 over 1 plus, this is xk, x squared k squared. So k is, so I have here 1 minus x squared to the square over x squared sine square KL times x. KL times x. T of x. So we may try to plot x with respect to T of x, but let's have a qualitative understanding of it. When x equals 1, that means K1 is equal to K, no reflection, and in fact, no problem. We have a unity there for the transmission coefficient. And let's take a value for KL. Roughly, let's say KL is, let's say 4 pi. And KL x n is equal to n pi. That makes 0. Let's take the next one. Is n plus 1 pi. So delta x, namely how often do we get these resonances? Delta x is, we subtract, that's pi over KL. That's pi over 2 pi over lambda L. K is the K of mu1, mu. So it is K, K1. So pi is cancelled. So it is lambda over 2 over L. So if, for example, KL is 4 pi, that's 2 pi over lambda L. Pi is cancelled. So lambda over 2 divided by L is 1 over 4. So delta x is like 1 over 4. Namely, at every 1 over 4, we have a transmission resonance. I took, remember, just arbitrarily KL to be 4 pi. So this is x. That's 1. We don't need these anymore. We need delta x equals 1 over 4 and that formula. Let's make it bigger. Delta x equals 1 over 4. Delta x equals 1 over 4 with KL is equal to 4 pi. K is the K of that thing. So let's take here. Let's take 2 and 3. So we have a transmission resonance at x equals 1. And then at every, so let's divide 3, 2. So here I have these transmission resonances. So you would expect it to go like that. And why does it get deeper? Because let's look at here. If x is very big, then this is like x to the 4. This is x square. This goes as 1 over x square. Sine square is at most 1. So whenever it's not 1, it is going down to 0. So these will be the transmissions. And again, and as x goes to 0, you can ignore this term. And then we have the sine square. It goes as 4 pi x altogether square. So squares cancel. But there's a big number that is killing the strength. So something like this. Okay. 1, 2, 3. These are getting deeper. So this is T of x. There is something interesting in this problem. We discussed the reflected wave here and the transmitted wave. But what about here? Don't we have a reflected wave here? Indeed, we do. So let me just show it. I'm erasing. We are done with the transmission coefficient. I'm erasing everything. So this is mu, this is mu1, this is mu. So at x equals 0, we have an incoming wave, I incoming, feeding, and I reflected going out. Now here, part of it will be transmitted into this, let me call it I plus, and well, again, there will be something that's coming from this one. So this will be I minus. This is x equals 0. This is 0 and L. Looked at from x equals L. I plus feeding it, the reflected wave at I minus, and then there's the transmitted wave. Clearly, these are all energy waves, okay? Energy currents. So I plus, what goes in equals what comes out. So I plus is equal to I minus plus I transmitted. Therefore, I plus minus I minus is I transmitted. Energy transmitted. Look to here, the feeders are incoming energy current and the I minus energy current. So I incoming plus I minus, that's equal to outgoing ones. I plus I reflected. Take it to the other side. I incoming, that's equal to I plus minus I minus plus I reflected. But we just showed this is I transmitted. Okay. And that's why if you divide by I incoming, 1 is equal to T plus R. This is the justification of our finding T as 1 minus R immediately. We didn't have to solve everything. But to find, if you ask what is I plus, what is I minus, then we have to solve for the coefficients here. And for example, psi2, we will write then alpha e to the I k2x plus beta e to the minus I k2x. So alpha will be alpha absolute square multiplied by this kinematic factor will give the alpha square will give this I plus, beta absolute square will give this I minus. Okay, so this is the discussion of the energy current and the conservation of energy current, conservation of energy, and the way energy divides itself between the reflected and transmitted waves. Thank you.